Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, how are you? I hope all of you is in good condition. In this meeting, in this section, I will explain about mathematical induction. But before I explain about it more deeply, I have something to share. Do you know Dominus effect? Dominus effect can easily be visualized by placing domino upright, each separated by small distance. Upon pushing the first domino, then the next domino will knock over and so on until there is no domino left standing. Look at this video. In mathematics, there is a technical proof. There is a proof technique that have some principle with Dominus effect. We call this as mathematical induction. Mathematical induction is proof technique. It is essentially used to prove that a statement holds for every natural number n. Note that this mathematical induction can only use to prove the statement that in natural number, not in real number. Suppose I have this statement. The sum of n consecutive odd number is n squared. If I write it down, 1 plus 3 plus 5 plus 7 and so on until plus n, 2n minus 1 is equal to n squared for n greater than or equal to 1, with n is element of natural number. How we prove it? For example, for n is equal to 1, 1 is equal to 1 squared. It is true. For n equal to 2, 1 plus 2 times 2 minus 1 is equal to 2 squared. 1 plus 3 is equal to 4. It is true. But we cannot substitute each natural number to this statement because we have infinite natural number. So if we just substitute it, the proof is not general. So we use mathematical induction. How to prove it using mathematical induction? Before I explain about it, I will explain what is mathematical induction. So, mathematical induction consists two steps. The first is base case, or sometimes we say it basis. And the second is induction step. What is basis and what is induction step? So, base case is we prove the statement for n equal to 1 or n equal to 0. But actually, base case is not always begin with n equal to 1 or n equal to, but it can be any fixed natural number. But as long as the number that we use is in the interval of the statement. And the next, so it is for n equal to 1, or maybe with n equal to 0 or n equal to 2 and the other natural number. And the second is induction step. Induction step is assuming that the statement hold for n equal to k. Assume that the statement true for n equal to k, then it is true for n equal to k plus 1. So, induction step, we assume that the statement hold for any fixed number. If it is true, then the next case is true. So, this induction step is true. So, in induction step, we assume that the statement is true for n equal to k, then it's true for n equal to k plus 1. So, this induction step is true. Yes. So, to understand it more, I will give you an example. Oh yeah. Actually, mathematical induction can we use to prove a formula, divisibility, and inequality. But I will explain how to prove formula using mathematical induction first, and for proving inequality and divisibility using mathematical induction, I will explain it later. So the first, for example, it is example how to prove formula using mathematical induction. So suppose Pn is 1 plus 3 plus 5 plus 7 and so on until 2n minus 1 is equal to n squared for n greater than or equal to 1 with n is element of natural number. This is a problem that I give you in the previous. How to prove it? First, for base case, look at this interval. This interval is for n greater than or equal to 1. So we can use any natural number as long as it is greater than or equal to 1. But if the interval here is n is greater than or equal to 4, so we cannot use 1, 2, or 3. We only can use 4, 5, and greater than 4. Suppose I take n is equal to 1. 1 is equal to 1 squared. Is it true? Yes, it is true. So the best case, so we have done for the best case. Because best case is true, we move to next step, that is induction step. For induction step, we assume that Pn is hold for n equal to k. Assume that pk is true. So we will assume that pk is true, then we will use this assumption to show that pk plus 1 is true as well. So pk is true, we get 1 plus 3 plus 5 plus 7 and so on until 2k minus 1 is equal to k squared. So it is true. Then we add both sides by 2 times k plus 1 minus 1. 1 plus 3 plus 5 plus 7 and so on. 2k minus 1 plus 2k plus 1 minus 1 is equal to k squared plus 2 times k plus 1 minus 1. The left hand side become 1 plus 3 plus 5 plus 7 and so on until 2k plus 1 minus 1 is equal to k squared plus 2k. 2 times k is 2k, 2 times 1 is 2 minus 1, so we get plus 1 like this, okay? Then 1 plus 3 plus 5 plus 7 and so on until 2k plus 1 minus 1 is equal to, look at this, this is equal to k plus 1 square. Look at the last equation. This is pk plus 1. So pk plus 1 is true, because by assuming pk is true implies that pk plus 1 is true as well. So this induction step is true, and because Pn is true in base case and induction step, so Pn hold for every natural number n greater than 1. So this statement is it has been proven. So we will move to another example, that is how to prove divisibility using mathematical induction. For example, prove that five divides 11 to the power of n minus 6 for n is greater than or equal to 1 and n is element of natural number. Suppose Pn is 5 divides 11 to the power of n minus 6. As I explained before, in proving this, we use mathematical induction and we do the first one, that is base case. We use n equal to 1. N is equal to 1, so P1 is 5 divides 11 minus 6. 5 divides 11 minus 6 is, it means that 5 divides 5. it is true. Because base case is true, we move to the next step, that is induction step. Assume that PK is true. Because PK is true, so it means that 5 divides 11 to the power of k minus 6. 5 divides 11 to the power of k minus 6. It means that 11 to the power of k minus 6 is equal to 5 times something. 5 times m. For m is element of natural number. From this we get 11 to the power of k is equal to 5m plus 6. We multiply both sides by 11. We get 11 to the power of k plus 1 is equal to 11 times 5m plus 6. From this, to the power of k plus 1, we subtract both sides by 6. Minus 6 is equal to 11 times 5m plus 6 minus 6. 11 to the power of k plus 1 minus 6 is equal to 55m. This is 66. 66 minus 6 is 60. To the power of k plus 1 minus 6 is we can write it as 5 times 11m plus 12. Look at this one. Because 11 to the power of k minus 6 can be written as 5 times something. So we can say that 5 divides 11 to the power of k plus 1 minus 6. So 5 divides 11 to the power of k plus 1 minus 6. Look at this. This is pk plus 1. If it is pk, so it is pk plus 1. It is pk plus 1. So pk plus 1 is true because pk is true implies that pk plus 1 is true as well. So this statement is, so this induction step is true. And because this statement is true in base case and induction step, so this statement is true for every natural number greater than 1. So this statement has been proven. We will move to another example, that is proving inequality using mathematical induction. For example, one plus 2 square plus 3 square plus 4 square and so on until n square is greater than n cube over 3. As I explained before, we assume that this statement is Pn. Let Pn is 1 plus 2 to the power of 2, 2 square plus 3 square plus 4 square and so on until n square is greater than n cube over 3. For the first is base case. Oh yeah, it is for n greater than or equal to 1. N is element of natural number. The first one is base case. We use n is equal to 1. Oh no, we use n is equal to 2 because in the two examples before I use n is equal to 1. So in this example we will use n is equal to 2 for the base case. For n is equal to 2, 1 plus 2 square, no. For n is equal to 2, P2 is 1 plus 2 square is greater than 2 cube over 3. This is 1 plus 4 is 5 greater than 8 over 3. Is it true? If it is 8 over 3, so if we change it into fraction, we will get 15 over 3. 15 over 3 and 8 over 3 is, this one is greater. So this statement is true. Then we move to the next step, that is induction step. Suppose assume that Pk is true. Pk is true. So 1 plus 2 square plus 3 square plus 4 square and so on until n square is, oh I'm sorry, this is not n but k. K square is greater than k to the power of 3 over 3. Then we add both sides by k plus 1 to the power of k plus 1 square. 1 plus 2 square plus 3 square plus 4 square plus and so on until k square plus k plus 1 square is greater than k cube over 3 plus k plus 1 square. The left hand side become this 1 plus 2 square plus 3 square and so on until k plus 1 square is greater than k cube over 3 plus k plus 1 square is k square plus 2k plus 1. The left hand side is the same, 1 plus 2 square plus 3 square and so on until k plus 1 square is greater than, we make the numerator the same, so it becomes k cube over 3 plus 3k square plus 6k plus 3 over 3. The left hand side is the same, 1 plus 2 square the right hand side become this, k cube plus 3k square plus 3k plus 1 over 3 plus 3k plus 2 over 3. The right hand side become k cube plus 3k square plus 3k plus 1 plus 3k plus 2 over 3. It is the same, we just make 6k becomes 3k plus 3k and 3 becomes 1 plus 2. Okay, so 1 plus 2 square plus 3 square and so on until k plus 1 square is greater than, look at this, k cube plus 3k square plus 3k plus 1 is equal to k plus 1 cube plus 3k plus 2 over 3. Remember that k plus 1 cube plus 3k plus 2 over 3 is greater than k plus 1 cube over 3. Do you know why? Because a plus b is greater than a if b is greater than 0. Not that k here is natural number, so it is positive number, so 3k plus 2 over 3 is positive number, so this one is greater than this one. So because this one is greater than this one and this one is greater than this one, do you understand what I mean? Suppose it is a and it is b and it is c, a is greater than b and b greater than c, by transitive we get a is greater than c. So 1 plus 2 square plus 3 square and so on until k plus 1 square is greater than k plus 1 cube over 3. Look at this inequality. This inequality, if Pn like this and this inequality like this, so this is pk plus 1. So this is pk plus 1. So pk plus 1 is true. Because by assuming pk is true implies that pk plus 1 is true as well. So this induction step is true. And because Pn is true in base case and induction step, so Pn is true for every natural number n. Okay. So this statement is proven. Okay, I think it is enough. That's all what I can deliver to you. I hope what I explain and what I deliver to you can be useful for us. Thanks so much for your attention. Assalamualaikum warahmatullahi wabarakatuh.